So, hello everybody. Welcome to my presentation about ventilation concept in classrooms. I will present you a result of a long-term study in 3 elementary schools in Germany. This is the work of my fellow and PhD student Susanna Bording, and my name is Arno Dentel. I'm a professor here from Nürnberg Tech in the field of building services engineering. So what was the motivation? The project was already a bit from the corona pandemic motivated, but when we look at schools, we see it's often too cold or too warm. The children are feeling sick. They are tired regarding perhaps the air, and we measured often a very stuffy air in these classrooms. So we compared the influence of different ventilation concepts on good air in classroom in these projects to have very happy children here, like in these pictures. So we measured good air quality, means also low CO2 levels. We measured and asked the children for the well-being and thermal comfort. And the ventilation concept has the aim to reduce the airborne diseases, and they should be more energy efficient than window airing. Our study compared 3 different ventilation concepts. On the first picture you see on the left border of the slide, the school with natural ventilation. The rooms have very big sliding windows there, and all classrooms are equipped with air sensor, with airing light. And my observation was in the school that the children are very motivated to jump out of the chair and go to the window and to open the window when the air light jumps from green to orange. And we had here 4 classrooms in the study. And the second concept was a retrofitting concept. It was a decentralized ventilation concept. And in that school, we observed 2 classrooms. And the last concept is a school with a central ventilation concept, with a central AHU. And we observed here 2 classrooms. In the red circle, you can see the air outlets of the central ventilation system on the right border, and in the middle picture, you see like a big box. So this is the central ventilation unit, and with a small duct with some outlets here. Our field study was from October 23 to April 24. And we want to check the influence of the illness of the children. And we focused here on elementary schools with children in the age between 7 and 11 years, because we think they don't have so much contact out of the school to other groups. And we also monitored in a long-term monitoring the physical parameters, and we cannot log the energy demand of radiators. We only logged the energy demand of the air handling unit, and so we extrapolated or simulated the data for the total energy demand for the 3 different concepts. So what have we measured? What parameters have we measured in the classroom? As I already mentioned, we measured the physical parameters. You can see that here in this picture: the temperature, the relative humidity, CO2, VOC, and PM 2.5. And we also measured and recorded the opening state of the windows. And we also measured the URTIS parameters. URTIS means upper respiratory tract infection. So we mounted a letterbox in the classrooms, and the children filled out a questionnaire when they were ill and bring it back to this letterbox, and so we can monitor the absenteeism of the children. We also monitored the temperatures of the decentralized air handling units and the centralized air handling units, and also the electrical energy demand of the fans and the electrical energy demand of the reheaters in the decentralized air handling units. In the classroom itself and in each school, we have a monitoring concept. On the left side, you see the outdoor weather station. We are measured the temperature, the radiation, the particle matter outdoors. Indoor, we measured with a compact station the humidity, temperature, CO2, VOC, and we also measured the window state with a small switch here you can see. All is transmitted to a Raspberry Pi and sent via a LTE router to our office once per day. So we collected a lot of data with a time step from 1 minute. The entire study period was 7 months, which means 213 days and 120 school days. We considered also the weekends, vacation, and public holiday days of 93 days and correlated with the occupancy time at school and 6 hours per day, school day and school break. We had 720 school hours for our data collection. So here are some results of the indoor parameters. I will concentrate here in this presentation on CO2 and on indoor air temperature. In these box plots, you see the different ventilation concepts on the x-axis of the diagram, with NV for natural ventilated, DV for decentralized ventilated, and for CV for centralized ventilated classrooms. I have a detailed look on the next slide for you regarding the indoor air temperature. When we compare the natural ventilated concepts, we have around 80% of the time temperatures below 20 degrees, and that means the natural ventilated classroom has the lowest temperatures and also the largest temperature spread when you look at the box plot, yeah? Because you're opening the window in autumn and in the winter, and a very cold temperatures come into the classroom. The decentralized ventilation concept, these are the green box, has the smallest temperature spread, and only 10% of the time is the temperature indoors below 20 degrees. Significant is also that the centralized ventilation concept or classrooms has the highest temperatures. You can see that on the purple box. And we have only 0.4% temperatures below 20 degrees. We also made at 3 different times in this period a visit at the school classes and asked the children, how do you feel? Yeah? How do you feel regarding temperature, regarding wind, regarding your personal motivation and so on? And regarding the temperature, I present here the outcomes of the survey. And what we see is that the natural ventilated rooms have a drift that the children say it's cold. Yeah, temperature of the room slightly cool, temperatures of your hands slightly cool, temperatures of your feet, temperatures of your head. It's okay for the natural ventilated schools or rooms. And what we also see for the central ventilated rooms, they are slightly warm. Yeah? Warm regarding the room temperature, also the hand, also the feet, and also the head. Yeah? This is a result of the CO2 concentration. We see that the natural ventilated rooms have good to acceptable values of the CO2 concentration. That means that nearly 24.7% the CO2 concentration is below 1000 ppm. The decentralized ventilation concept has the best values. However, we have here very high outliners. You see that in the diagram with the red marks. I will explain it on the next slide. Why is that? And the centralized ventilation concept has high CO2 levels and also high outliners. I will also explain that on the next slides. So we come to the decentralized ventilated rooms, which means classroom 1 in blue and classroom 2 in orange. We see some big peaks over 2000 and also maximums of 3000 ppm. And we have here installed a decentralized ventilation system. And so we asked why, as we saw the monitoring data. And then we had a deeper look. We correlated the electrical demand of the air handling unit. And we saw that the air handling unit is not running at occupied times. It is running in the night. It was the wrong time schedule installed at the air handling unit. So it's a fault here. And mid of October, you see the CO2 concentration measured and the electrical demand of the ventilation system is at the same time. So we adapted the time schedule for this. Yes, I already said that we have incorrect time settings in these systems. It is not running at the day; it's run in the night, and also the switching time from winter to winter time was 2 weeks too late. And the air handling units were also switched on too late after the vacations, or they also switched off too early before vacations. In the centralized ventilation system in these two rooms, we observed very, very high CO2 levels and peaks, and we asked us, why is that? And they told us that the supplier is controlled there by CO2 and by presence sensors. But we had also a look in the monitoring data of the building itself, and we find out that they also observe the window state, and when they open the window, they shut off the mechanical ventilation system. But nobody knows that till this project. So they have no mechanical ventilation in that time that they open one window. So we saw that also out of the window opening times in the natural ventilation group, the windows are open twice as long as in the mechanically ventilated concept. In the centralized ventilation group, they mainly opened one window, and it was tilted during the average ventilation time. And this was the reason this one window that the system was shut off. And the summary of that is that the natural ventilated group has good to acceptable CO2 levels. They have big windows with sliding ones, and they have CO2 traffic lights. However, they have also the lowest temperature and the widest temperature spread regarding the room temperature. The decentralized ventilation group has the best CO2 levels when the setting of the AHU is correct, and the centralized ventilation group has CO2 levels that are rather high because of this energy efficient control strategy that the users didn't know about that. And we saw in all concepts that the relative humidity is rather low, and it was especially low for the mechanical ventilated classrooms. So I will conclude on this slide. Correct settings of the ventilation systems is not a matter of course. Decentralized and centralized ventilation system must be controlled and operated correctly. And the users need to know about special control settings. And more information about the long-term monitoring, about the physical data, you will find that in a publication, in a paper from Susanna, which is published last month. And we also investigated a correlation between the comfort and the medical data. And we published there a paper in December, and it is at the moment under review. So thank you for your attention. I hope I'm in time at this late afternoon, and I want to thank Zukunft Bau for supporting us with this research project.